straight away, but because of this new YouTube setup, we can. So we should just do it. Welcome. It's an iGCSE electricity lesson. It's the last iGCSE electricity lesson. All right. Next term, after 2 weeks off for Easter, we're doing waves. So we need to sort of recap some stuff and check you've understood stuff. And also, there's two different kind of companies, right, that could do your iGCSE physics. There's Pearson/Edexcel, or there's Cambridge. We've covered everything that Edexcel want you to know, but Cambridge need you to know like just a couple of other things. So we'll quite briefly cover those. And in my Facebook group, as usual, I'll send you some links to some places that explain it very well, I think, and we'll give you some questions on it. The first thing we need to just quickly do, because Cambridge, I'm just going to mention it for you, and then you can sort it out yourselves later. Cambridge needs you to know about something called EMF, right? What is EMF? Well, it stands for electromotive force. EMF stands for electromotive force. And the units of EMF are joules per coulomb. Are you seeing a problem? Do we see a instantly, if you've been doing the last 10 electricity lessons, you should be seeing a little bit of a problem here. What's the problem? Electromotive force. Electromotive force. And it's not a force, is it? Clearly it's not a force. If it was a force, then the unit would be the Newton. And it is not. No. What is it if it's measured in joules per coulomb? What must it be? Joules per coulomb. It's a voltage, right? Joules per coulomb. Another way of saying joules per coulomb is the volt. So it is a voltage. It's a potential difference. It'll make more sense, this, when we've done energy. So we haven't really studied energy yet. But instead of saying energy, you can say work. Okay? If you do work on something, it kind of means you sort of use energy up. We'll talk about energy later, but what EMF is, like in a nutshell, if you picture this, I'm going to draw a cell on the board and then I'm going to constantly refer to it as a battery. Sorry, not sorry. Batteries, right? You attach wires to them, they've got electrons in them, electrons which are attracted to the positive side of the battery and repelled by the negative side of the battery. So the electrons travel from negative to positive, yep, even though that's not what convention says. The battery keeps the electrons moving, right? So what the battery needs to do is to sort of shift the electrons over to the negative side again, so that they can be repelled by the negative side, right? If the electrons just flowed from the negative side to the positive side and then stopped, then it would be a very short battery life. So what the battery does is it does work on the electrons, like it moves them over. It's kind of chemistry on the inside, so we're not going to talk about that. But the battery doing work on the electrons to get them over to the negative terminal is what we call the EMF. It's the amount of energy per charge, right? As the battery does its thing. I'm not going to talk any more about that, actually. The only thing I'll say is that, well, you might be able to tell me the equation for EMF. So I've told you that the units of EMF are joules per /coulomb. So what's the equation for EMF? Well, it's kind of the same as the equation for voltage, right? It's energy divided by, that's what that slash means, charge. Because energy is measured in joules and charge is measured in coulombs. But when you look at this, because they will, if you're doing the Cambridge exam, they will give you the equation in the booklet they have announced, I believe. It won't say energy, it will say work, which, sorry, is a bit annoying, but it'll make more sense, like I say, when we do energy. So the symbol for energy is a W, and the symbol for charge is a Q, you remember that? So that's the equation for EMF, electromotive force, which isn't a force, it's a potential difference, sort of within the battery, work divided by charge. Right, I'll try and remember to mention it again when we do energy and work done and things. Okay, the other thing, which in my mind is more fun, that Cambridge want you to learn about is something called a variable potential divider. That's a lot of words that we don't use in real life. To talk about it, I'm just going to be a slightly indulgent parent for a second and show you a circuit that my 4-year-old built the other day. My 4-year-old, every time she comes home from school, my electronics kit is on the side because I've just been talking to you about it. So she's been playing with it, right? Like she had 3 LEDs, you remember light emitting diodes that only allow current to flow in a certain direction, and she had a battery pack and she was putting the LEDs in the circuit, and she was looking at how if you use 1 it's really bright, but if you put 2 in then they're much dimmer, right? And if you put 3 in they don't even light up. How would you explain that to my 4-year-old? She's 4. One bulb shines really brightly, 2 bulbs they're a little bit dimmer, and 3 bulbs they don't light up. What are you going to say? Go on, take 10 seconds. Just say it out loud. You done it? You think that? Yeah, you think she'd be happy with that? What I was talking about, I just sort of said, oh yeah, well it's because the battery gives them energy. The battery is giving energy to the loop of things. And when there's 1 LED, then it doesn't have to share. It gets all the energy to itself. But when there's 2 LEDs, then they have to share. And when there's 3, then they really have to share, and there's hardly any energy left, so they don't light up. So then she built this circuit, okay? Battery pack, switch, bulb, it's my 6-volt bulb, yeah. And this, which is a little motor, but you put this sort of propeller thing on top of it, and so it becomes a fan, okay? And she switched, what do we think we're gonna see, all right? So this is a 6-volt bulb, and it's 3 volt, those batteries are pretty well charged, so it is about 3 volts being given by the battery. What do you reckon? Quick, 3, 2, if you made a prediction about what the bulb's gonna do and what the fan's gonna do, let's turn it on and see. Is that what you got? So look, the bulb is lit up, right? But it's very, very dim. So this must be a complete circuit. There must be a current flowing all the way around, obviously. If there were any breaks in the circuit, then it wouldn't work. This motor is working. It's not a broken motor, but it's obviously not working. And she was like, why isn't that working? And I had to explain to her in terms of sharing of energy. And then she changed it, and she did fix it, bless her. So we'll talk now about sort of what is happening there and how she fixed it. Okay, right, this is the last time I'm going to mention this, because you know the Institute of Physics who teach physics teachers hate this model, but I'm just going to briefly go there, I'm sorry. We have looked at how circuits are a little bit like pizza delivery motorbikes going round to a party. So you could say that a pizza shop delivers pizza to a party, and it gives pizza to motorbikes that sort of travel around this circuit here and deliver the pizza to the party and then come back empty and pick up more pizza. We've said before, slightly shamefacedly, that if this was a circuit, then the charges would be the bikes, the energy would be the pizza, right? The battery gives energy to the charges which flow around, and the voltage is the amount of energy per charge, right? So voltage is, in this case, the amount of pizza per bike. So this would be like a 1-volt pizza shop, is that all right? It's giving 1 joule of energy to each charge. And if we add another pizza onto each bike, then we've got a 2-volt pizza shop, yeah? 2 joules of energy per charge. So this bulb would shine brighter, okay? I'm just massively mixing up my pizzas and my circuits here. I'm just going to stop apologising. If you add another party, an identical party to this circuit, what's going to happen? Well, the pizza gets shared, right? Equally, because both these things are identical. So you get 2 joules of energy per coulomb. 1 joule of energy is delivered to the first party and 1 joule of energy is delivered to the second party. Shush, I don't know. So remember, we've sort of said before, pizza never goes back to the shop. All the pizza has to get delivered to the parties. And I've written, this is why you have to be careful with LEDs, because they're tiny parties. So if they get too much pizza, they melt or something. Okay, we will never talk about pizza ever again. But you know what I mean, right? If you've got a tiny little LED that barely needs any voltage to work, and you put a 9-volt battery in your circuit, the LED can't go, oh no, sorry, just a little bit for me. It has to take all the joules per charge that battery is giving it, and will probably melt. So if I show you this, I'm thinking you will not have any problems with this. We've got a series circuit with a 6-volt battery in it, 2 identical bulbs, and voltmeters across each bulb. I'm hoping you could tell me pretty much straight away what the voltage across those bulbs is, what each voltmeter is going to say. 3, 2, 1. Hopefully you said 3 volts each, yeah? They're identical bulbs, so they're sharing the voltage. And if I told you the total resistance of this circuit was 4 ohms, then what's the resistance of one bulb? 3, 2. The total resistance of the circuit is 4 ohms. What is the resistance of one bulb? It's, yes, 2. It's not a trick question, okay? Because the bulbs are identical, right? So it's equally hard for current to flow through them, and they're sharing the voltage equally. So it's hard for the, obviously, 2 bulbs in series. It's harder for current to get through than just one bulb on its own. In fact, it's twice as hard, okay? So hopefully no surprises there. So here's a circuit where the voltage is being shared equally. I'll just do this one as an example. You've got a battery. We don't know what the voltage across it is, but we've got 2 6-ohm resistors in series. An ammeter, we don't know the reading on it, but we know that the voltage across each resistor is 5 volts. So what's the voltage across the battery? What's the total resistance of the circuit? And what's the reading on the ammeter? I've said this is an example, but I'll give you 10 seconds, see if you can scribble down an answer or think about what the answer is. One of them is quite easy, but the other one's like a little jump, I think. Actually, it's pretty easy, isn't it? All right, I'm just going to go for it. The voltage across the battery is just obviously all the voltages added together, which is 10 volts. And the total resistance of the circuit, you just add the resistances together, yeah? So the total resistance, you've only got 2 things, so it's 12 ohms. So you can work out the reading on the ammeter using this little equation here, the V equals IR, yeah? If voltage equals current times resistance, you want current is voltage divided by resistance, and then you could do a couple of things. You could use the overall voltage of the circuit, which is 10 volts, and the overall resistance of the circuit, which is 12 ohms. Divide 10 by 12 and you get 0.83. But it's a series circuit, right? So so the current is the same everywhere. So you could also do just the current flowing through like one of these resistors. Sorry, that's my dishwasher, I'm going to have to stop it. So you could have just done 5 volts divided by 6 ohms, okay? Because that would tell you the current flowing through that resistor, but because it's a series circuit, it would tell you the current flowing through the whole thing. Wow, there's something like slightly ironic about being massively disturbed by a dishwasher during an electricity lesson. All right, you have a go at this then. This one's harder. I must admit, I really like these little puzzles. I'm glad we get to go through this. Thanks, Cambridge. You've got a series circuit with a 6-volt battery in it and 2 resistors. One of the resistors is a mystery, but you know that the voltage across it is 2 volts. And one of the resistors is 2 ohms, but you don't know the voltage across it, and you don't know the current flowing through this circuit. So can you tell me, please, what's the voltage across the 2 ohm resistor? So the 2 ohm resistor, what voltage has it got across it? What's the reading on the ammeter? And what's the value of the first resistor? And if you finish that, then the hard bit, a bit of revision. How could you build a circuit, pretty much identical circuit, but you've got to swap out like one thing so that the resistance of one component could be changed? How do you build a circuit so that it's like that, but the resistance of one component could be changed? There's a few different things you could do. I'll give you 12 more seconds. Basically, just sketch as many things as you can think of that you can change the resistance of them. We did this not that long ago. Like, maybe if they heat up, or if you shine light on them. I've said too much. Okay, let's go through it. So the voltage across the 2 ohm resistor, hopefully that one wasn't very difficult, right? You've got 6 ohms, 6 volts being provided by the battery, and 2 of those volts are across the mystery resistor, so there must be 4 volts across the other resistor, right? The reading on the ammeter, oh, I love this stuff. So you might have thought, okay, I'll just do voltage divided by resistance, and the total voltage is 6, but you don't know the total resistance, right? This one resistor is a mystery. But you do know the resistance of this resistor and the voltage across that resistor. So you can work out the current flowing through that resistor, and then that tells you the current everywhere, right? Because it's always the same. So you can just do 4 volts divided by 2 ohms, which is 2 amps. So that's the ammeter reading. And the value of the first resistor, well, now you know the current flowing through the first resistor, and you know the voltage across it. It's all come together. So resistance is voltage divided by current. So you do 2 volts divided by 2 amps, and you get 1 ohm. Splendid stuff. Right, so why is this related? Why do Cambridge need us to know this? Well, this is a very boring version of a circuit that can divide voltage across components, okay? But it's particularly useful if you can change the voltage across one of the components. So I was asking you, how are you going to change the voltage of one of these components? You would have to change the resistance by using maybe one of these. Do you remember a light-dependent resistor and a thermistor? What do you mean, no? Well, it's a chance to revise them, isn't it? That's the whole point. I am going to show you an incorrect diagram of a thermistor later on, so let's just focus people and remember that this is the correct one. It's, I don't know how you remember that. It's a little stick person's foot, isn't it, standing in front of a resistor. And which foot is it? It's its right foot, or maybe it's a little, I don't know. Let's carry on. Right. Let's put a thermistor in this circuit instead, okay? Let's start simple and say that, first of all, they've got exactly the same resistance. So they're sharing the voltage equally, okay? They're basically identical as far as the circuit's concerned. The thermistor gets hot. What happens when a thermistor gets hot? You remember? Its resistance. What happens when a resistor gets hot? Are you remembering that? I'm going to flip it. You remember a thermistor? It's made of semiconducting materials, right? So a thermistor gets hot. That means that the particles in it get more energy, and it kind of loosens up some of the electrons in the thermistor so that they can flow. So that's more current, right? So if you've got more current flowing, you would say that it's easier for the current to flow. So its resistance has decreased. We got there, well done. So let's say that its resistance has gone down to 3 ohms now. Because more electrons freed up to flow. So if its resistance decreases, it's easier for the current to flow. So they sort of need less of a push. In my daughter's words, it's being less greedy. So this doesn't look right anymore, just intuitively does it? If these now are different things, they're not going to be sharing the voltage equally. And you might be able to see what happens. So can you see that the thermistor's resistance is half of this resistor's resistance? 3 is half of 6. So what do you think these voltages are going to do? Okay, you've got a 9-volt battery. How is that 9 volts going to get shared across the 3 ohm thermistor and the 6 ohm resistor? Like you would expect, basically. It's 3 volts and 6 volts. And the current, because the thermistor's resistance has dropped, then the whole overall resistance of the circuit has dropped. So don't forget, current is changing as well. If the resistance of this circuit is lower, then the current has increased. Is that okay? Whew, right. So finally, we have got here a circuit that can vary how the potential difference is shared across it like this. Like this thermistor could get hotter and colder, and its resistance would change, and therefore the voltage across it would change. This kind of circuit is called a variable potential divider, which is what Cambridge would like you to know about. Here, this is from your spec. You have to recall and use the equation for 2 resistors used as a potential divider. It's not as scary as it sounds. Here's the equation. R1 divided by R2 equals V1 divided by V2. So to give you an example of how that works, you would just label, say it was 2 resistors in series like this, you would label one of them R1 and R2, and then V1 and V2 are just like the voltages across them, right? So the V1 is the voltage across the R1, and V2 is the voltage across the V2, okay? So let's have a look at just a quick example. R1 divided by R2 equals V1 divided by V2. So in this situation, what is R2? You've got, apart from, yes, very nearly a character from Star Wars. People got very distracted on Facebook yesterday talking about Star Wars at this point. So R1 is 6 ohms, but R2, we don't know. The voltage across the 6 ohm resistor is 3 volts, and the voltage across the R2 is 2 volts. What is R2? What is it? A lot of people were just sort of looking at this and working it out yesterday, which is great. If you can just look at it and work it out, can you also use the equation just to check that you are using the equation correctly? Because this is some tricky rearranging, I think. Especially because R2 is on the bottom here, so you need to get R2 on its own, which is weird. in my non-mathematical opinion, it's weird, isn't it? As usual, there is at the moment on my Facebook homepage a post saying, if you're watching live on YouTube, feel free to say hello here. So if you want to say hello or ask me any questions that have been bugging you about electricity over the last 10 weeks, then please do. Excuse me. Have you got on? Right, let's have a go at rearranging this equation then. You need to get R2 on its own, and R2 is on the bottom over here. So we need to, if we're dividing on this side, we need to times on the other side. So I'm going to put V1 divided by V2 in brackets and then just times it all by R2. So we've got R1 on its own. We want R2 on its own. So if we're timesing by V1 divided by V2 on this side, we've got to divide by all that on the other side. So you end up with R1 divided by V1 divided by V2 equals R2. Whew, we got it on its own. And then we just plug the numbers in, okay? So R1 is 6 ohms, V1 is 3 volts, and V2 is 2 volts equals R2. So the answer ends up being hidden by my PowerPoint, end up being 4 ohms. A lot of you could just look at that and say, oh, okay, well, here, you could just say, okay, the voltage is half of the resistance, so it'll be the same on that side. But well done if you actually worked it out using the equation. Fabulous. So, what's the solution? What did my 4-year-old do when her motor wasn't working and she really wanted it to go around? Well, I said, oh yeah, the problem is, love, I think that motor just hasn't got enough energy because, you know, they're not the same thing, so they're not sharing equally, and that motor isn't getting enough energy. And she went, oh, I'm going to go and find a bulb that isn't so greedy. And I don't know if she'd read the numbers on the bulb, but luckily for her, the only other bulb I've got is a 2.5 volt bulb. So she did, bless her. She went and got a different bulb that she was hoping wouldn't be so greedy. And she turned it on again. And lo and behold, can you see that? The motor span around. And then her mother broke it. So that's good, isn't it? And you can see the bulb's a bit brighter as well, right? Because they're sharing energy in such a way that they've both got enough to work. Splendid. Okay. Shall we do a little recap then? So electricity can be really difficult because quite often you think you've understood something and then you get a certain question and you realise you haven't understood it at all. Like this happened, I remember when we were in the staff room at the school that I was a teacher in, there was a certain A-level electricity question where all the teachers, except for one, who I used to just follow around the playground asking questions, were like, what? What? Like, even physics teachers can come across questions where they're like, I thought I knew that, and I didn't know that. So I've tried to write you some of those questions. Here we go. I've drawn some circuits, and I just want you to tell me, will the bulbs light up? So I'll be very disappointed if you don't get at least one wrong. I need to try and find the bits that you haven't understood. Okay, here we go. So, yes, you've just got a series of bulbs. The only thing I have told you is that, you remember an LED? Yeah, LED, a diode that happens to emit light. The long leg of an LED, if you're looking at the real one, not the circuit diagram, the long leg is positive and the short leg is negative. Okay, so all the bulbs are identical and assume that no diodes are melting. The first circuit is a cell with a wire going from the positive terminal to the negative terminal and a bulb in the middle. Is that bulb going to light up? The second one, you've got a loop of wire going from the positive terminal of a battery back to the positive terminal with a bulb in the middle, and then the same, another loop of wire going to and from the negative terminal with a bulb in the middle. Are those bulbs going to light up? The third one, you've got 2 cells in a row and a wire is going from the negative terminal of one to the positive terminal of the other with a bulb in the middle. Is that bulb going to light up? The next one, you've got a bulb that has just sort of been positioned on the side of the battery, like where the plastic coating is, but one side of the bulb is touching the positive side and one side of the bulb is touching the side of the cell that's called the negative side. F, you've got two loops of wire going from the positive terminal to the negative terminal of a cell, but one of them, and only one of them, has got a bulb in the middle. G, you've got an LED with a long leg touching the positive terminal of the cell, and the short leg is wired up to the negative terminal of the cell. Is that going to light up? H is exactly the same, but it's the short leg of the LED attached to the positive terminal of the cell. I, you've got a circuit symbol for a light emitting diode, and the triangle, which is part of the symbol, is pointing towards the negative terminal of the cell. And J is exactly the same, but the triangle is pointing towards the positive terminal of the cell. K is just a series circuit with a bulb and a voltmeter in it, and a cell. And L is exactly the same, but the bulb and the voltmeter have switched places, so the voltmeter is on the side of the negative terminal. And M is a series circuit with a cell and a bulb and an ammeter in it. I'll give you 20 whole seconds to get finished off. Okay, draw my circuit on the board, and then I'll flip you around. Okay, let's go through them. Number one, or A, wire connected to either side of the cell with a bulb in the middle. Yeah, that's totally fine, isn't it? Number two, hopefully you said for B and C. No, that is a nonsense. Electricity is a flow of charge, isn't it? It's charges moving. And if a wire is connected to a positive terminal and then back to a positive terminal, there's no potential difference there, is there? There's no reason for the electrons to flow because they're going from positive to positive. Why would they move? And D, well done if you said no, that is nonsense as well, because it's not a complete circuit. You need to have a circuit connected for current to flow, like for it to be a complete loop. E, no, that's definitely not going to work either. I thought I might trick you because like one side of the bulb is slightly touching the bit labelled positive and negative, but obviously that's just a plastic coating. It's this metal terminals here that you'd actually need to wire it up to. F did cause a lot of people a lot of problems. On Facebook, a lot of people were telling me that F would light up. F will in fact not light up. This one with two wires, and one of the wires has a bulb in the middle. It's probably worth flipping you for that one. The reason that F will not light up is that current takes the path of least resistance. Now, it takes quite a lot of energy, it's quite a lot of work for current to flow through a bulb, right? Bulb's got quite a high resistance. Wires have hardly any resistance, kind of the whole point of a wire. So electrons flowing, charge flowing through this circuit, they will pretty much all choose to take the path of least resistance, which is just the wire. Some of them will go through the bulb because, like, if they've got a choice, you know, some of them will always go through this one, but this one won't be getting enough energy to light up. No way. This is what we call a short circuit, by the way. If you sort of have a connection across a cell or a battery or power supply, that doesn't have any component in it, that's a short circuit. It is a very bad thing. So when, like, you know, you get like fraying wires or something and they accidentally connect together, that generally means that the thing stops working. So well done if you said that F would not work, and I'm kind of pleased if you did, and now you know. Right, G, this one was really hard actually, because we've been talking about like positive and negative things attracting. That is the one that would light up. You attach the positive leg of an LED to the positive terminal of a battery. It's kind of telling you, attach this to the positive end. So H, which is the opposite, that one wouldn't light up because the negative leg is attached to the positive. But well done if you just said that those two would be different. Like, well done if you said, well, one of those would light up and one of them wouldn't light up. But now you know, positive leg to positive terminal. This one, you remember the way that current flows conventionally? So we know that electrons flow from negative to positive, but the convention is they flow from positive to negative. So this one is going to light up because the diode's pointing in the right direction, right? Just checking. You all remember what a diode is, don't you? A diode is a thing where if it's got a forwards bias, if it's pointing in the forwards direction, its resistance is very low, so current can flow. In fact, loads of current can flow often, which is why you need to put a fuse in with the diode. But if you turn it around, it's got a really, really high resistance, so basically doesn't allow current to flow. Yeah, that's what a diode is. So a light emitting diode is just something that does that and happens to give off light. This one, well, this light emitting diode, the arrow is pointing towards the positive, so current flows from positive to negative, so no, this is going to have too high resistance, it's not going to light up. K foxed a few people as well, I was kind of pleased to see. K is definitely not going to light up, and nor is L. Why not? Why are K and L not going to light up? You see that now? Quite a few people had forgotten how voltmeters and ammeters go in a circuit. So a voltmeter has got a really, really high resistance. Imagine you've got a bulb here. You've got a voltmeter measuring the measuring the voltage across the bulb. It's got a really high resistance, right? Because you don't want current to choose to flow through the voltmeter because that would affect the circuit, okay? The voltmeter's only job is to measure. So the voltmeter's got a really, really high resistance because it sort of wants to be like, no, current, you just go through the bulb, like pretend I'm not even here. So yeah, high resistance means not much current chooses to flow through this wire. So you're not affecting the circuit that you're measuring. Which does mean that if you attach a voltmeter in series, this circuit will have a huge amount of resistance and the bulb probably won't light up yet because not enough current will flow. So that's why that one wasn't working. And M, it's totally fine, isn't it? It's just a normal circuit. Ammeters have a very, very low resistance so that current can flow through them so that they don't affect the circuit as they measure current flowing through them, all right? Phew, well done. Okay, just in case that wasn't enough for you, I've got another classic set of questions. Here's a circuit. It's just a cell and a bulb, and the bulb is shining normally. So all these bulbs are identical. If we change the circuit slightly in all these different ways, can you say if these bulbs are shining more brightly or just normal, the same, or are they dim or are they out? So bulbs A and B are in a circuit with just one cell. So it's basically the first circuit, but you've just stuck another bulb in. C is the same circuit again, but the cell has been turned around. So now the bulb is sort of nearer to the positive terminal and not nearer to the negative terminal. Sorry, not the positive terminal. D and E, that's also a series circuit with two bulbs, but now we've added another cell as well. So it's two cells and two bulbs. F is exactly the same as the first circuit, except the wires are shorter. And G is the same as the F circuit, but the wires are longer. I should say, by the way, if you want some scale, let's just say it's basically this circuit here, okay? It's just a kind of like kids' school electronic kit style setup. So that's the scale we're working on. H and I are a parallel circuit. So it's like the same circuit as the normal one, but we've added another branch on of wire and we've put a bulb in there as well. And J, it's another parallel circuit, just the same, except another branch doesn't have a bulb on. So it's like a series circuit with a bulb, and then you've just put a branch of wire across the bulb again, but there's nothing there. And K is the same, but the wire without the bulb is in between the cell and the bulb. Whereas in the other one, it goes bulb and then wire. Phew. And if you've done that, I've got some tasty little multiple choice questions for you. What units make up a volt? What units make up a volt? Is it J per S, J per C, C per S, or C per J? What units make up a watt? What? Is it J per S, J per C, C per S, or C per J? And what is that? It is drawn. Is it drawn incorrectly? Yeah, it is, isn't it? Well, regardless, is it a variable resistor or an LED, a thermistor or a fuse? That little boring old rectangle with a stick person's leg in front of it. And what is it about a thermistor that changes when it heats up? Is it its voltage, its resistance, or the amount of light it emits? All right, let's go through it. And the bulbs A and B, well, if a bulb lights normally when it's got one cell, then if these two bulbs are having to share the voltage from this battery, they are going to be dimmer. And the next one, it's just the same, right? I was hoping that I wouldn't confuse you by just turning the cell round. It doesn't matter which way the cell round is, not a diode, it's just a bulb. D and E, well, you've got two bulbs, but you've added another cell. So you've sort of doubled the resistance of the circuit, but you've also doubled the voltage. So that is absolutely fine. They're both working normally. And F, I was a bit worried that, because we've talked about how long wires have a higher resistance, I was a bit worried that I might have confused you into thinking that if you just shorten the wires a bit, then the bulb might shine brighter, right? Because there's less resistance. No, that bulb is going to be normal. So obviously, like in this circuit here, it doesn't make any difference whether I use like this length of wires or twice the length of wires or even 4 times the length of wires. You're not going to notice a difference in how bright the bulb is on that scale. So G was just going to work normally as well. And H and I were also going to light up normally. That's a bit weird, isn't it? You remember how voltage is the amount of energy per charge. So whether the charges flow through that bulb or through that bulb, they're still providing the same amount of energy per charge. So those are both shining normally. J, did you spot that that's a short circuit? So that bulb is going to be out because the current has got a choice of where to flow, and it's going to almost all of it choose to flow through just the wire because there's very little resistance there. So it's just going to go through the battery, out, back into the cell again. You're going to run out the energy in your cell very, very quickly, and that bulb's not going to light up. And the same with K as well. That is pretty much going to be out. What units make up a volt? So that's a joule per coulomb. Well done, we've just done that. And the units that make up a watt, we did that quite recently. Do you remember that's joules per second? A watt is a unit of power, how much energy something uses up per second or shifts per second. That is a thermistor, we just did that. And what is it about a thermistor that changes when it heats up? It is its voltage. Oh, no. Don't make me go through all this again. There we go. Right, just a couple, I won't do this very, I'll do this quite quickly, but I want to try you on this first question in particular. A set of 10 Christmas lights in series is plugged into the mains electricity supply in the UK. If 0.2 amps flows through each bulb, how much current flows through the circuit altogether? What is the resistance of each bulb? And what is the total resistance of the circuit? And number 2, you've got 3 batteries. They're each connected to identical bulbs. Which battery makes the bulb shine brightest? And can you explain your answer? So you've got quite a slender battery, which is 1.5 volts. A fairly large battery, like medium-sized battery, which is 9 volts. And you've got a very big, wide battery, which is 3 volts. Which one of those are going to light a bulb the brightest, and why? Can you sketch, please, a fuse, a resistor, a diode, and a power supply? And I've got you 3 graphs on the bottom. Can you tell me what components might these graphs represent and finish labelling them? So you've got current on the y-axis and potential difference on the x-axis for two of them, and one of them's just a straight line going through both, and one of them it's a very flat line which sort of suddenly goes up. And the last graph is for a bulb, and it's a sort of shallow S-shaped curve, but can you label the axes for me? Where's current going to go and where's voltage going to go? The first one's really evil. It's a really mean kind of trick question. Did you get that? All right. If you've got a set of 10 Christmas lights in series and they're plugged into the mains electricity, if it's a series circuit and 0.2 amps flows through each bulb, then the current flowing through the circuit is still 0.2 amps. Is that okay? That was so mean, wasn't it? Because in a series circuit, the current is the same everywhere. You don't add up the current. It's just if the charges are flowing at a certain rate per second, then they are. You know, if the charge per second is the same thing. It's 0.2 amps, okay? The resistance of each bulb, well, you know that V equals IR, okay? So resistance equals voltage divided by current. If resistance equals voltage divided by current, you had to remember that the mains electricity supply was 230 volts, and then divide that by the overall current, which is 0.2 amps. So that gives you a resistance of 1,150 ohms. But, okay, you've done the total voltage, haven't you, divided by the total current. So that's giving you the total resistance of the circuit. But actually, there's 10 bulbs. So for the resistance of one bulb, you do need to divide that by 10, yeah, because the total resistance is being shared by 10 bulbs. So it's 115 ohms was the answer. Don't worry if you didn't get this. I think it's just really hard, but it's good brain exercise, isn't it? So the total resistance of the circuit, you have just worked it out. It's 1,150 ohms. Well done if you said that size doesn't matter at all, and it's the battery with the highest voltage, or the cell with the highest voltage, I should say, which is going to make the bulb shine brightest because it's giving the current the most push, or it's got the most energy, providing the most energy per charge. Sketch the following. All right, let's do this. Did you remember the difference between a fuse and a resistor? So a fuse is a boring rectangle, a resistor is a boring rectangle, but the fuse has a line going through it. Ooh. A diode, I think Alice explained this very well on Facebook the other day. She was like, oh yeah, it's just a pizza in a box with a line going through it. Fine, I'll take that. It wasn't a light emitting diode, right? If it was giving off light, you'd draw a couple of arrows. But don't do that if they... I mean, I suppose it's still a diode, isn't it? But and a power supply, did you remember that? That was ages ago. Power supply is like two lollipops looking at each other. There you go. We'll do a bit more on that as we look at electricity in another module. And finally, these graphs. That one was a resistor. You remember? Because... current and potential difference are directly proportional because the resistance is fixed. This one was a diode, because current doesn't flow at all in one direction and it does in the other direction. And this bulb, well, the resistance, when bulbs are on for a bit and they get warm, if it's a filament bulb, then their resistance increases. Do you remember? As like the wire in a bulb gets hot, there's more collisions between the electrons and the particles in the wire. So this one, you wanted, oops, it was just the same. You wanted current up there and voltage on the x-axis, because voltage increases, the push increases, but because the resistance has increased, the current doesn't go up, okay? So it's just the same as these ones. Phew! Right, I'm going to flip you around. So that was it wasn't really our last electricity lesson, actually, because probably next year, after we've done quite a bit more, we get to look at things called transformers and like electricity cables and how electricity gets to and from our homes and how electricity is generated. It's nothing like our last electricity lesson, but it's the last one of this module. So we've got a 2-week break now for the Easter holidays. I will give you, as usual, plenty of like extra reading to do and past paper questions that I found. Although, to be honest, you should be able to answer pretty much all of them by now if you want to have a look for yourself in my Facebook group. So go and have a look at that. And yeah, I'm so excited that after half term, after these holidays, we get to study waves. So we're going to be looking at diffraction and reflection and lights and rainbows and sound waves and all that stuff. It's going to be very cool. Okay, I'm just on my Facebook page to see if anyone's left me any comments. If you have not left me any comments, you might want to stay around because people do have a habit of asking very good questions. Oh, no comments at all. Well, that's all right then. Clearly you've all understood everything. Yeah, wow, that's the first time that's happened. I need to start putting these posts up further in advance. Okay, thank you so much for coming, you lot. If you want to support me, you know you can. There's like a link in the About section. Click it and I'll send you loads of nice things. Other than that, have a lovely Easter. If you like this sort of thing, I'll be doing my Lego Storytime on YouTube tomorrow at 2 p.m. About eggs, and we'll be learning all about how eggs work. If you bring some ground up eggshells and some vinegar and a bottle and a balloon, then we will be looking at like how eggs work, what eggs are, the chemistry of eggs, basically. If you're not an egg person, just bring bicarbonate of soda instead. Okay, thank you so much for watching, you lot. I'll see you very soon. Bye!